Now the bad way to do things. I have a directional coupler. Assume that this is a 3 dB coupler. Let's do this assumption. Okay, I know that this is 3 dB. So if my input power is 1, so if, sorry, this is 1, here my output power is 1/2 and 1/2. Okay. Then I have a delay line, and I put this Phi1, Phi2. This is completely wrong. Why? Because this is power. It's not the complex amplitude. It's not the amplitude of the field. Okay? So I cannot mix something that is power, and power by definition is real, because when you take this square modulus, everything you have becomes real. Okay? And then I add the phase. So never do like this. Keep the phase till the end. Not one step, square modulus, one step, square modulus, one step, square modulus, doesn't work. Okay? Maybe this can sound you trivial and stupid, but be sure that some of you typically fall down in this kind of mistake. Okay? So now what I have to do is the proper way to proceed and to multiply our matrices. Okay? So we have to multiply this by this by this to find out what is the output of our device. By the way, this object, this guy, has a name. Is a particular example of interferometer. One of the simplest, because I have just two beams interfering. Okay? And the name of this guy is Mach. Never remember what H goes, should be here. Zender. Interferometer. Okay. Okay, so we can cancel this and more. Oh, so this means that this is L1 and this is L2. Okay. So I will skip over all the calculation because nothing interesting to tell. But at the end of the day, let's assume that our input E1 is equal to 1. So this is the field amplitude, it's not power. In this case, they consider. And E2 is 0. So let's assume that we are injecting a signal just from one input port of our Mach-Zehnder interferometer. And what I'm interested to see is the transmission from my input port 1 and output port 2. And then when I arrive at the end, here I take the square modulus. Physically is what I measure if I put a photodiode at the end at port 2 of my interferometer. just to measure the power, the intensity, okay, at the end. So I calculate this by cascading the matrices, by making the product, I give you the result, and let's go commenting the result. And here this happens like, this looks like this. I write, then I comment. Okay. So we already defined these two. So these are the two terms related to the splitter and combiner, so K and LC. And then delta phi is basically phi1 minus phi2. Okay, and in case I have, so it's beta delta L, and so it's 2 pi divided by lambda, effective index of the two waveguides that are assumed to be identical, delta L. And this is the delta phi we discussed a lot yesterday, okay? And so everything I told yesterday about the phase difference between the two signals interfering applies to this specific case, okay? So this is the key parameter of our interferometer. So let's write also in this way, 2 pi f divided by c. The power that I measure at this port depends on a lot of things. These parameters related to the directional couplers, and then all the parameters we saw yesterday in our preliminary discussion. So it depends on the frequency, depends on the effective index of the waveguides, depends on the geometrical unbalance of the interferometer. All these things. Okay, so let's give a name to the output port of our interferometer. You see here that I enter from this waveguide and I'm looking for the expression of the power at this output port. So I have changed my waveguide, okay? Waveguide 1, waveguide 2. So I'm crossing the structure, and so typically O2 square when the input is I1 is called power at the cross port. So the power at the cross port of the interferometer is the port, okay, of the waveguide I'm not entering from. While if I enter from port 1 and I look at the output 1, so I remain on the same waveguide, this power is typically referred to as P bar. Okay? Just to give a name to the port. Crossing means I go to the other waveguide. So, if I want to use this device as a filter, so a filter is something that, for instance, allows you to drop a signal from one waveguide to another waveguide, I should be able to do one thing, first of all. And this thing is I should be able to transfer all the power from this input port to this output port, okay? So I should be able to have unitary transmission from I1 to O2. So if I look at this, if I look at this, that is the product of a cosine and a sine, and both functions are never greater than 1, it means that if I want this to be 1, both of them should be able to be as high as 1, okay? So let's start from this. So how should I design my directional couplers in order to be able to transfer all the power from one waveguide to another waveguide? So this guy should be 1. So the argument to KLC should be pi half. Okay? That means that KLC should be this, or I'm telling always the same thing. Okay. So this means that it is not possible to have this unitary power transfer with any kind of directional coupler. I need a directional coupler satisfying this relation, and if you go back to chapter 2, you see that this means that my directional coupler has to be a 3 dB coupler. Okay, so it's possible to have this complete power transfer only if my directional coupler, this guy, is 3 dB. 50-50. That is not really surprising. And it is the reason why most of the times that you look at a device like this, you have 50 directional couplers, splitters. First condition. Then look at this. This has nothing to do with the directional couplers. This is just related to the delay lines. So if I want this cosine to be 1, I need delta phi half to be pi plus and pi. Okay, that means that the phase difference, here there is a 2, that is not an option, because delta phi is 2 pi plus 2 m pi. What does it mean? It means that if I build my Mach-Zehnder interferometer with these building blocks, so if I use 3 dB directional coupler here, a 3 dB directional coupler here, and I put in between 2 delay lines, I have unitary transmission. That means all the light coming from this port out goes from this port when these two delay lines basically introduce the same phase shift, because writing 2 pi or a 2 pi multiple means that when I split my field, and I have a phase relation here. After this trip, they arrive here with the same phase. So basically, these two delay lines do not modify the phase relation between the two fields. Okay? But pay attention, since delta phi is related to the frequency, depends on the frequency, it means that I will have certain frequencies at which delta phi is 2 pi. And this means that if my input signal has this frequency, is completely transferred to this port. In contrast, if my input signal has a different frequency, this condition is not satisfied and it goes elsewhere. Where? It depends. If this is not a 2 pi multiple, but is a pi odd term, so if the relative phase shift is pi, this goes to 0. Power disappears from this port. There's no loss. Where does the power go? Up. Okay. So by modifying the phase relation delta phi, what I see is at the output ports that the power goes here or goes here. Okay? And this may happen when I change the frequency, but this is not the only option. Whatever thing is going to change this term delta phi, whatever I do that changes this delta phi is going to modify the power split at the output port. Okay? This means that if I change the effective index, if I change the geometrical imbalance of an interferometer, I'm going to change the power split ratio at the output port.
So it's impossible to use a Mach-Zehnder interferometer in a multi-mode fiber?
Why? Multi-mode waveguide.
Why?
Okay, so now the question is, everything I have written holds for a single mode waveguide. Where is the problem if my waveguides are not single mode but multi-mode? Here you have all you need to answer now. Let's make a picture and I'll help you. So this means that if here I have my frequency axis and here I write my P cross power, so I just make a plot of this function when this guy is 3 dB, so when this is 3 dB, this is 1, disappear, and so let's simplify like this, okay? So for a Mach-Zehnder with 3 dB couplers, it reduces to this, very simple. So it's just the output power changes as a square cosine with delta phi. Delta phi depends on the frequency, so along the frequency axis, what I have is if I have no loss, this is 1. So these are the frequencies. Let's go call F0. F0 plus what? The period is the free spectral range. So This is another frequency at a distance that is the free spectral range. And the free spectral range has exactly the expression that I gave you yesterday for a generic interferometer. Okay? So, this is what I should expect if I put a photodiode, a power meter, here at my output port. I have one at the input, I change the frequency, and here what I see is the power that goes here, 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 here periodically. Okay? So, what is going to happen if my waveguides are no more single mode? Assume that here inside, instead of a single mode, there are two modes. No ideas? So this means that if at the exam we will give you an interferometer with a multi-mode waveguide, we will be happy as well. No, you are going to get crazy.
F1 different from F0 and
F different.
F1 different from F0 and
Two-mode waveguide means that I have an input signal at a frequency f. So the frequency is defined from the source, from the laser. Okay, so it's f for both. The difference that if I have a single mode waveguide, all the power will travel in the waveguide with the shape and with the properties of a single mode. Yes, but only one mode. If the waveguide is multi-mode and I have another mode, okay, it means that I put the light inside and that the light inside can propagate on the first, on the second, on both. Okay? And is it a problem here? Which is the parameter here in the blackboard that is going to change if I have another mode? Good. This. Each mode propagates with its own speed, its own phase velocity, its own beta, its own effective index, all synonymous. So, when I write this, what should I consider? Nef of mode 1 or nef of mode 2 or both? Both. I mean, I will have two modes inside propagating and they are, let's say, orthogonal. Okay, so it means that this interferometer will have to work for both. So the conditions that I have written here, this and this one that has disappeared, must be fulfilled for both. So first problem, to realize a 3 dB splitter that splits the power 50-50 for both the first mode and the second mode. It's not easy. But the worst problem is this. Because these two guys, these two modes will have different nef. And you have, if you want to transfer all the power here, okay, at this frequency, you want to transfer all the power at this port, you have to match the delta phi equal to 2 pi condition for both. And it's not easy. So, people, 99.99 periodic % of time, choose to work with single mode waveguide because in this way there is only one degree of freedom that has to be managed. That is the beta, the net of the single mode, of only one mode. Otherwise, you have to satisfy these conditions for all the modes. So, this is, if this is clear for this guy, okay, the reason is the same for any other device that you will see in this course. Because this is the simplest, okay, and even though this is a simple device, working with two modes is extremely hard. So when you will see much more complex structure, you will understand better why. Okay, so is it clear now? So single mode waveguides are useful because they make your life easier. However, you should know that it is not always possible to have only one mode, because you have to deal with what? Polarization. So it is easy to design a waveguide that propagates only the first TE mode without propagating the second, third TE modes. Okay? But most of the time, when you have the first TE mode, you have also the first TM mode, because they are very close, so it's very difficult to make a waveguide. It's possible, but it has some drawbacks. So what you have to do to deal typically is with a waveguide where actually you have beta TE and beta TM. And sometimes you cannot avoid this. Sometimes you have to work with both. And this is the reason why one of the worst problems for photonic integrated circuits is to make them polarization independent. Polarization independent means that if you change the polarization of the light here, so if here you have TE or TM or a combination of the two, you would like this guy to make exactly the same thing, to be polarization independent. Okay? This is what people that buy your circuits ask for. Okay? When you look at the data sheet of a component, one of the key specifications is polarization dependency, polarization dependent loss, because they want this circuit to be polarization, all the circuits in general to be polarization independent. Okay? So this means that this has to work for both polarization, and both polarization means that you will have inside two modes, because two polarization are basically two modes with beta that are typically close to each other but different. And in this case, you cannot avoid to work with both, and you have to optimize the design. It's easy, in this case, it's easy to do this. It's easy to make a splitter that split the light equally for both polarization. Okay, so this does not scare me much. But when I have to do this in my life, I don't sleep very well. So delay lines that delay the same for TB and TM. This is just a comment on modes and polarization. Is this clear? Then, so far, so good. We have worked with ideal components, but we have to also consider non-idealities that can typically appear in real life. Let me think where it's better to cancel. Maybe here. 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 let me rewrite this. Equals to KL. Okay? So ideally, I told you that this circuit has a periodic frequency response. So ideally, you should see this shape, this sinusoid versus frequency forever. But someone would argue that, for instance, this 3 dB coupler in practice will not be able to split the light 50-50 at any wavelength. Is something surprising you, or you believe that it is difficult to do it? Do you have a physical explanation why, if I change the frequency in a directional coupler, so this is my directional coupler, at this frequency, if I'm a good designer, I do it in a way that 50 of the power goes here, 50 of the power goes here, okay? At this frequency. Then, what is going to happen if I change the frequency? So this is realized, it's fabricated, so I cannot change anything more of this. But I want to use it at a different frequency. Okay? So is this 3 dB splitting maintained at any frequency? The answer is no. I already told you. Why? Do you have any physical explanation to explain me why the splitting ratio of this device is going to change if I use it at a different frequency?
I think because the coupling,
No equations, just physical and explanations.
maybe because the coupling coefficient depends actually on the frequency. So in
Sure. So here, what is going to be frequency dependent is this. Good answer. But why physically K is frequency dependent? Change with the wavelength.
Because we have to compare the dimensions to the wavelengths, maybe,
The dimensions of
the directional coupler, the piece of the directional coupler with the wavelength
the
of
distance between the waveguides, D.
K depends on the distance between the two waveguides. Okay, but the distance is frozen, is there, does not change. Okay?
Yes.
The waveguides are like this.
Yes.
I change the wavelength of my signal. Why the coupling should change? Let's make a zoom. So this is my directional coupler, is one waveguide, is another waveguide. What happens here? I have the modes of this waveguide that partially overlap with the modes of this waveguide. Okay? This happens at one frequency. If I increase the frequency, how should I change this picture from a qualitative point of view? So the waveguides are the same, do not change. So if I tell you, okay, I increase the frequency, and the mode is going to become broader, like this. So if I make this design, it means that there is higher overlap, and so if there is a higher overlap, K is going to be bigger or lower? Bigger. Okay, but is it correct that if I increase the frequency, the overlap is bigger because the mode is broader? If I increase the frequency, the mode is broader or is narrower?
Wavelength it reduces, so
The wavelength reduces,
yes,
so the wavelength goes down,
so narrow, I think.
it narrows. Okay, so if I increase the frequency, I reduce the wavelength. This is not a good picture. The good picture is this, more confined. And if the modes are more confined, they talk each other less. So my coupler, that if this is the picture of my coupler, and I put here the frequency axis, and here I have my 3 dB split. I make the design here at F0. I change the frequency, and what I should expect is something like this. Okay, no equations. That means that I move from the 3 dB condition, and the 3 dB condition is the condition that in a Mach-Zehnder interferometer allows to transfer completely the power from this port to this port. Result is that if I move from the frequency that I have optimized, I cannot expect any more unitary transmission to this port. So this means that actually what is going to happen is that here is like this, but little by little I see something like this. Goes down. Okay, so this envelope on both sides. Okay, because on this part I'm coupling less than 3 dB. On this other side I'm coupling more, but in both cases I'm deviating from the 3 dB condition. And so the picture is horrible, but what I expect to see is something like this. Okay? So this always goes to 0, but the peaks are no more 1. So this is the effect that you expect due to the wavelength dependence of the directional coupler. The effect that you observe in the transfer function of a Mach-Zehnder interferometer. Shall I go ahead? Okay. So, this is because what you have to do in practice is to deal with realistic objects. So, you have to consider that if you change the wavelength, something is going to change in your device. Just a couple of comments on this. So, a Mach-Zehnder interferometer, let's say by definition, is an interferometer where you have typically 2 arms, okay, so 2 branches, and then you have a 2x2 splitter and a 2x2 combiner. Okay, but sometimes, for instance, in this case, we only inject the light from one port. So we didn't use the second input port of the interferometer. This means that in practice, what you could use instead of a directional coupler is a 1x2 Y branch. Okay, do the same just replacing the 2x2 directional coupler with a 1x2 Y branch. Then what shall I put at the output? It depends. Here I can use both this or this. So in practice I can use as a combiner a directional coupler if I need to collect the power from both output, but I can also do something like this. Okay, so it's 1x2, 2x1. Mathematically, what I have to do is replace the transmission matrix of a directional coupler with the transmission matrix of the Y branch that you should know. And just let me do two comments. First, do you remember what is the main difference between, if I want to use if I want to realize a 3 dB coupler, do you remember what is the main difference between using a directional coupler and a Y branch? So what is the difference between these two guys, assuming that they both split the light 50-50?
The dependence on the wavelength.
This is a good point. It's a good point. The wavelength dependence is expected to be different, and typically, if I want a lower wavelength dependence, this could be preferable because the split ratio 50-50, because of the symmetry of the structure, is maintained. If you change the frequency, maybe what is going to happen here is some additional loss. So you have again 50-50 splitting, but it's not 50% of the input. Maybe you have, if you change the frequency, you have 48 and 48. So it's still a 3 dB splitter because the output is the same, but you have some power that is lost, but it's still balanced. So one option from practical point of view is to use a Y branch if I need a balanced splitting over a broader wavelength range. This is a good point. There is another difference. That is more conceptual than practical. If I write here, this is the power, okay? 50-50, 50-50. Some information is missing. And the missing information is the phase. Always. It's a nightmare. So, is there any difference between the phase between these two guys in a 3 dB splitter and these two guys in a Y branch? Again, the phase is not an option. I don't know if you have been told to focus on it, but in a 3 dB Y branch, because of the symmetry of the structure, the phase is the same. They share the same phase, okay? Delay is the same, the phase is the same. So if I look at the phase difference between these two ports, the phase difference is 0. Is the same in a directional coupler?
Depends.
Good answer, depends. Okay, if I have a 3 dB synchronous directional coupler, the most simple that you can imagine, the phase shift is, they are in quadratro, okay? So this delta phi is pi half. And when I wrote this delta phi between these two, delta phi between these two, let's put here, sorry, a tilde so we make a difference. Okay, so this delta phi is the phase difference given by the splitter, while this delta phi as before is the phase shift given by the delay lines. When I wrote this relation, and I told you, if delta phi is 2 pi, all the power from this port goes to this port. Is it true? Is it true? But this happens when my splitter and combiner are realized in this way. Because what matters, don't forget, and you will see this very well moving to more complex architecture, is the total phase shift. So imagine that you have input beam is divided in two. So you have an initial phase shift. This initial phase shift is pi half in a directional coupler. So there is one of the two that is already delayed. So there is an initial delay. While here they are in phase, no delay. Then you add these delay lines. So it's something that adds to the initial delay, but the initial delay matters. Okay? So what you have to do is to sum all the phase delays that are experienced during the travel. And so, if you replace this with a Y branch, pay attention that this relation does not give you any more unitary transfer to this port. You can check it mathematically. But without using the equation, the reason is that it's the total phase shift that matters. And if you have a different initial phase shift, pay attention that the phase shift that your delay lines have to introduce to send the power where you want, you desire, can be different. Okay, so just to conclude this, if I have designed this interferometer very well, so that the light goes at the output where I want, and then I oh wait, but I'm using only one input port. So no, why this? I replace with this because this is less wave independent. Big mistake. I have to rearrange something here because I have changed the phase shift at the beginning. Okay? This was the first consideration. That the second one is this. Before okay, so this is the transfer function of a Mach-Zehnder interferometer, what we drew before, the P cross versus frequency. So this is the power that goes at this port. The power that goes at the other port, if I have no loss, is just complementary. Okay? So the solid line is P cross and the dashed line is P bar. I change the frequency and I swap the power from one port to the other. Okay? But what happens? This is for this guy. Okay? What happens here? If I use Y branches, so I have my input power that is 1, and I move across the frequency, and I just look at this P out. I have only a single waveguide, and I want to measure the light here. So if I make all the calculations with the transmission matrices, I found that the shape is the same. Changing the frequency, I change the delta phi between these two arms, and what I see is this. So this means that periodically I will see the power appear here, up, down, up, down, up, down, like this. And what happens when I see no light here at these frequencies? Sorry, my phone is ringing. 30 seconds to think about it.
For maximum, the P cross is this one, which is this one.
For this and the power is for this. Yes. This for this and that one is for this. Thank you. So you should also change this.
This is for Alexander with a coupler.
Again, without making any calculation physically.
Because here you have both cross and bar, and you have cross and bar. But in this one, just
Thank you.
When I change the frequency, I change the relative phase. Okay? I change the relative phase of the light arriving at the input port of the Y branch. Does it matter or not? The phase, the relative phase at the input of a Y branch. Of course it matters. I told you, assume that, okay, yes. These are single mode waveguides, okay? Everything here is single mode. Only in the Y branch you know that the waveguide, sorry. In the Y branch you have something like this. So this is the Y branch, okay? So you have here a multi-mode section, okay? So, as I told you before, the phase relation between these two is, the phase shift is 0. Okay, so the light split in two parts with equal amplitude and equal phase. Okay, so this means that if I put here reflectors, what happens? There's these two guys. Go back and assume that everything is still in phase. And if I enter from the two-port side in the Y branch with equal phase, they add in phase and they build again my fundamental mode. Okay? But if now I play with this and I add a phase shift between these two, So a phase shift, let's say, can be like this. Let's say they are traveling in this direction, okay, but there is a pi shift between the two. What is going to happen? In the first case, the problem had an even symmetry. Everything was symmetric, even symmetry. Now the problem has no more an even symmetry because this has phase, a shape, this is a shape, and when they combine, they are no more exciting this because this mode has an even symmetry. They are going to excite who? The higher order mode, the second mode. Okay? Very qualitative description. This arrives from here, this arrives from the other side. And so they are exciting not the fundamental, but they are trying to excite the higher order mode, the second mode. But if this waveguide is a single mode, what is going to happen to this mode? Okay? If this waveguide is a single mode, this mode is going to be radiated away. So if I put my photodetector here, no light is arriving here. So the power, in this case, disappears from the output port because I have tried to excite the higher order mode.
Can you do the same drawing with the entire?
The entire scheme?
Yes.
So, single mode, fundamental mode, wide range. I split in two. Same phase, same phase. Okay, so what should I draw here? It depends on the relative phase shift. So, if delta phi is 2 pi, or a multiple of 2 pi, there is no additional phase shift, so here what I'm going to draw is the same. Okay, and in this case, they add with the same phase, and here what I get is power at the output is 1. So each time this number is a multiple of 2 pi, I get this, 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 this. Change the frequency, and I go here, or here, or here. That means, in this case, delta phi is pi plus 2 and pi. Okay? It means then that one of the two is the relative phase shift that matters, is reversed. And so I'm not going to excite anymore a field with an even symmetry, but with an odd symmetry. That is the sum of this plus this. So it's the second mode. And if this waveguide is single mode, is radiated. If this waveguide is not single mode, this can survive. Okay? Because if this waveguide is not single mode, is multi-mode, is a large waveguide that can propagate both this and this, this device is no more a filter, because is no more is no more a amplitude filter. This can be used to transfer the power from one mode to another mode. So if I put here a photodetector getting all the power from all the modes, the photodetector will always see power 1, because the power is not going to disappear anymore. So in this case, my photodetector here, if the waveguide is multi-mode, whatever the frequency, will see 1. If the photodetector is able to catch everything. But if I look inside this power, I will discover that there are some frequencies where this power is carried by the fundamental mode, other frequencies where this power is carried by the second mode. So I'm swapping the power from one mode to another mode. So if you play with the transmission matrices, you always get sine cosine function, okay? But you have to try to look at the physics behind. So what is going to happen physically? Is it dramatic? No. Okay, so I think we can have a break. I don't know what is your common strategy. A break now, 10 minutes or what you like, and then we can restart. And if you have any questions, so please ask.